All right, now we're going to look at a different kind of energy called potential energy. We use the word potential because it has the potential of doing work. So potential energy is a kind of stored energy. And then we will also talk about one of the most important principles in all of science, not just in physics, but in all of science, and that is the conservation of energy. So first of all, we want to define this term conservative forces. Now think about this situation. If you throw a baseball straight up in the air, as it rises, gravity does negative work on the ball and the ball will slow down. So the gravitational force will transfer kinetic energy from the ball. We now say that this energy is transferred by the gravitational force to the gravitational potential energy of the Earth ball system. So we need both the ball and the Earth for this to work, right? Because there's a gravitational force acts between the ball and the Earth. So it's one system consisting of the ball and the Earth. So as the ball rises, it eventually stops and then it falls back down due to the gravitational force. And during the fall, the transfer of energy is reversed. The work done on the ball by the gravitational force is now positive, and the force transfers energy from the gravitational potential energy of the Earth ball system to the kinetic energy of the ball. So for either the rise or the fall, the change in the potential energy in the Earth ball system is defined as being equal to the negative of the work done on the ball by the gravitational force. Okay, so notice the symbol delta U. We use the symbol U for potential energy. So delta U means the change in gravitational potential energy. So the change in the gravitational potential energy equals the negative of the work done by the force within the system. So our system now is the Earth and the ball. And so the force between the Earth and the ball is the gravitational force. So when I throw the ball up, the work done by gravity is minus mgh. It's negative because the force is down, the displacement is up. So gravity does negative work. That means the change in potential energy is positive and it increases. Right? Then as the ball comes back down, gravity is doing positive work, and so the negative of the positive means that the gravitational potential energy decreases. The change is negative, so the gravitational potential energy decreases. But the principle is that the change in the potential energy equals the negative of the work done by the force in the system. So that in the system part is very important. All right, we can also apply this idea to a block and spring system without friction. So here I have a block attached to a spring. Initially the block is located at 0 in the diagram, and that's the relaxed position of the spring. And if I abruptly shove the block, giving it an initial kinetic energy, the spring force then will act to do negative work on the block, slowing it down and transferring that kinetic energy from the block to the elastic potential energy of the block spring system. So it will compress the spring and store potential energy in the spring. So the block will slow down. Eventually it comes to a stop, and then it reverses direction and speeds up as the spring does positive work on the block. The energy is then transferred from the potential energy of the block spring system back to the kinetic energy of the block. All right, so now we're going to define conservative and non-conservative forces. So in our last two systems, the ball earth system and the block spring system, the system consisted of two or more objects. Second, we had a force that acts between the particle-like object in the system and the rest of the system. So in the first case, we had a particle like object was the ball, the rest of the system was the earth. In the second case, we had the block, and the rest of the system was the spring. 3. When the system configuration changes, the force within the system does work, and we'll label that W1, on the particle, transferring energy between the kinetic energy of the object and some other type of energy of the system, which we call potential energy. And then 4, when the configuration change is reversed, the force reverses the energy transfer, doing work W2 in the process. All right, so consider the first one when I throw the ball up in the air. So first of all, I throw the ball up in the air, and what happens to the ball? It gets higher up in the air, farther from the earth, and the gravitational force does work W1 on the ball. Then the ball comes back down, and the gravitational force does work W2 as the ball comes back down, reversing the energy transfer. So on the way up, the kinetic energy transferred into gravitational potential energy as the Earth did work 1, or the gravitational force did work W1. Then on the way back down, that energy transfer from potential back to kinetic, the gravitational force did work W2, transferring that energy from potential to kinetic as it comes back down. All right, so when we have a situation in which W1 equals the negative W2 is always true, then the other type of energy is potential energy, and the force is said to be a conservative force. So if the first work, W1, is equal to the negative of W2, if that is always true, no matter what path we do, then we have a conservative force, and our other type of energy is potential energy. So potential energy can only be defined for conservative forces. So whenever the work is independent of the path, we have a conservative force. So consider the ball in the earth again. When I throw the ball up, the gravitational force does work W1. And then as the ball comes back down, the gravitational force does work W2. Well, W1 equals the negative of W2. We had MGH, negative MGH on the way up, and we had positive MGH on the way back down. And so W1 equaled the negative of W2. If that's always true, we have a conservative force, and we can define a potential energy. So the gravitational force is a conservative force. The force by ideal springs is a conservative force. And we will see in the second semester of the course that the electromagnetic forces are also conservative forces. So some examples of non-conservative forces. Friction is a non-conservative force. Drag forces, which are a form of friction, are also non-conservative forces. So some example of a non-conservative force, consider friction. Now, if I have a long table and I put a book on one end of the table and I give the book a shove, and so it slides across the table. Well, what's going to happen? The friction is going to do work and slow the book down to a stop. Well, the book will not then suddenly reverse direction and come back to me, right? The friction will do work on the book and remove the kinetic energy. But where does that energy go? Well, it turns into heat, and then that heat just dissipates into the environment. I cannot collect that heat and put it back into the book and make the book come back to me. That never happens. And so friction is a non-conservative force. And we cannot define a potential energy for non-conservative forces. So there is no friction potential energy. There's no such thing. We can only define potential energy for conservative forces. So here are two important results. The first box, the net work done by a conservative force on a particle moving around any closed path is zero. So if we start and stop at the same point, the net work done is zero. The second important point is that the work done by conservative force on a particle moving between 2 points does not depend on the path taken by the particle. It only depends on the endpoints, the beginning point and the end point. It doesn't matter how we got from one place to the other. So the work done by conservative force is path independent. And then also the last one, potential energy can only be defined for conservative forces. And remember, change in potential energy equals the negative of the work done by the force in the system. Now that's key, the force in the system. So the Earth ball system, it's the gravitational force between the ball and the Earth. In the block spring system, it's the spring force between the block and the spring. So if I reach in and pull the block attached to the spring and move it around, I'm an external force. I am not a force in the system. All right, another thing that's important, which I'll mention here and we'll talk more later, is that it's only changes in potential energy that matter, that have physical meaning. So there is no absolute potential energy. It's only changes in potential energy that matter. All right, so how do we determine potential energy values? Well, consider a particle-like object that is part of a system in which we have a conservative force F. When that force within the system does work W on the object, the change in the potential energy, delta U, of the system is equal to the negative of the work done by the force. All right, so let's consider one dimension. The work, of course, is equal to the integral from position 1 to position 2 of f of x dx. This is the work done by the force as the particle moves from initial position x sub I to final position x sub f. The change in the potential energy then is the negative of this work. So delta U equals the negative of the integral of x initial to x final of f dx. So this is the general relation for potential energy. All right, so this integral then is how we define potential energy function. So delta U equals the negative of the integral from x initial to x final of f dx. Now we can extend this to 3 dimension by making these positions as vectors. So now delta U equals the negative of position initial to position final of f dot dr, where dr is our differential displacement vector. We can also write this in differential form. The du equals minus f dot dr. And again, the dr, of course, is dxi hat plus dyj hat plus dzk hat. And remember again, the force is within the system. Now let's apply these general forms to things that we know. So, for example, the gravitational force. Gravitational force we can write in vector form as minus mg j hat, right? With up being positive, down being negative. Then the change in gravitational potential energy equals the negative of the integral from y initial to y final of minus mg dy, which gives us, well, m and g, of course, we'll consider those as constants, so we can pull them out of the integral, and we get mg times the integral of y initial to y final of dy, which gives us mg times the quantity of y final minus y initial, or mg delta y. So this was our familiar mgh that we've used before. So if we take u initial equals 0 as our reference configuration and call that when y initial equals 0, then we have delta u equals mgy. All right, again, it's only changes in potential energy have physical meaning. So that means we can pick a reference point wherever is convenient for us. So if we just say the initial position is y equals 0, and we're going to call the initial potential energy there 0, then our change of potential energy is just mgy, where y is the distance we go from y equals 0. So the gravitational potential energy associated with an Earth particle system depends only on the vertical position or the height relative to some reference position. It doesn't depend on the horizontal position. So gravitational potential energy only depends on how far we are up, right? It only depends on the height relative to our reference. It does not depend on horizontal position. All right, now let's try the spring system, the block spring system. Okay, so considering a block spring system, the spring has a force constant K. As the block moves, the spring force, F equals minus Kx, does work on the block. Thus, the change in the potential energy then equals the negative of the integral from our initial x to our final x of minus Kx dx. K, of course, is a constant, so we get K times the integral of x initial to x final of x dx. And the integral of x dx, of course, gives us 1/2 x squared. So we have a 1/2 kx squared evaluated from initial position to final position. So 1/2 kx final squared minus 1/2 kx initial squared is our change in elastic potential energy of the spring, the block spring system. So if we choose our reference point x equals 0 as the equilibrium position of the spring, and we also say that when u equals 0, then our elastic potential energy as a function of position becomes 1/2 kx squared. So this is very useful for determining how much potential energy we have stored in a stretched or compressed spring. 1/2 kx squared, where x is how much it is stretched from the equilibrium position or compressed from the equilibrium position. All right, now we introduce another term, and this is called mechanical energy. And we use E with the MEC subscript. So mechanical energy of a system is the sum of the potential energy and the kinetic energy of the objects within the system. So the mechanical energy of a system is equal to the kinetic energy plus the potential energy. So when a conservative force within the system does work on an object within the system, that force will transfer energy between the kinetic energy and the potential energy, but the sum of the two is always constant. So when they're within my system, the sum of the kinetic energy and potential energy stays constant. If we only have conservative forces, then within our system, the change in the kinetic energy plus the change in the potential energy equals 0. So that's another way we can write that. So if our kinetic energy increases, that means the potential energy decreases by the same amount. And if our kinetic energy decreases, the potential energy increases by the same amount. Another way we could write that is if we know the kinetic energy plus potential energy at one point or time, we also know the kinetic plus potential at another point or time. So K2 plus U2 equals K1 plus U1. The sum of the kinetic and potential is constant. So this is what we mean by energy conservation. Energy conservation means the energy does not change. The total amount does not change. Now it can change between kinetic and potential, but the total amount stays constant. This is a very, very important principle. So if we only have conservative forces, the total mechanical energy cannot change. So just to summarize here, when the mechanical energy is conserved, we can relate the kinetic energy plus potential at any time to the kinetic plus potential at any other time without considering what happened in between. And we don't have to find anything that happened in between. We don't have to find the work done by any forces involved. If we know the kinetic plus potential at one time, that's going to be the same as the kinetic plus potential at any other time, no matter what happens in between. Also, when we're considering potential energy, it is only changes in the potential energy that have physical meaning. So we can always define Our 0 for potential energy is our reference point anywhere we find convenient. All right, let's look at an example with the gravitational force. Here we have a girl on a water slide. She starts at a height h, and she's going to go down the water slide to the bottom. And we're going to neglect any friction. So we have a child of mass m is released from rest at the top of the water slide at a height of 8.5 meters above the bottom of the slide. So neglecting friction, find the child's speed at the bottom of the slide. Okay, so when we tried to do something going down a ramp before using Newton's laws, we had to find the acceleration and then use kinematic equations. But now we can't do that. But knowing energy conservation, we can make this into a very simple problem. Since the slide curves and varies in slope, we won't be able to find her speed by finding her acceleration. But since her speed is related to her kinetic energy, we can apply energy conservation. We only have conservative forces, just gravity. We can relate her mechanical energy at the top to her mechanical energy at the bottom. So that means the change in her kinetic energy plus the change in potential energy must sum to 0, right? Since the total energy stays constant, any change in kinetic energy plus change in potential energy will sum to 0. So we can do that. Well, since she starts from rest, her kinetic energy at the top is 0, and thus as she goes down, the kinetic energy will increase. But also her gravitational potential energy will decrease since her height is decreasing. So we write that the change in k plus the change in u equals 0. The change in the kinetic energy is her final minus initial. Well, her final we'll write as 1/2 mv squared with a b subscript, meaning the velocity at the bottom. Her initial kinetic energy was 0 since she started from rest. So we have 1/2 mv bottom squared minus 0. The change in the potential energy is decreases since she decreases in height. So that's minus mgh. Those sum to 0. So we get 1/2 mv bottom squared equals mgh. The m divides out, so we don't even need to know her mass. And then multiply both sides by 2, and we get v bottom squared equals 2gh, or v bottom equals the square root of 2gh, or v bottom equals the square root of 2 times 9.8 times 8.5, and we get 13 meters per second. So that's how fast she's going when she reaches the bottom. Now notice how simple that is compared to what we did before. Now suppose we know the potential energy is a function of position, but we don't know what the force looks like. Well, we can find the force from the potential energy. So if I write the definition of potential energy in differential form, so we have du equals minus f dot dr, and assume we only vary in one dimension. Then, from the differential form, we can see that the force as a function of position is equal to minus du dx. So if I know the potential energy is a function of position, I can find the force by taking the derivative with respect to position. It's the negative of the derivative with respect to position gives us the force in that direction. Let's try that for a spring. So suppose we're given that the spring potential energy is equal to 1/2 kx squared. We can find the force by taking the derivative with respect to x and then take the negative of that derivative. So minus du dx gives us minus kx, which of course is the spring force. Gravitational potential energy we said was mgy, so the gravitational force is minus du dy, and we get minus mg, which is our gravitational force. All right, now we want to consider work done by a force that's external to our system. So, for example, if I have a block spring system and I reach in and I move the block around, stretching and compressing the spring, I would be an external force to the block spring system. So when we have an external force acting on the system, energy can be transferred to or from the system. So work by an external force or by an applied force is energy transferred to or from a system by means of an applied external force acting on the system. Positive work will transfer energy to the system, and negative work will transfer energy from the system. So now we have the work done by an applied external force. That's what the W with the A subscript means. The work done by an applied external force. That will equal the change in the kinetic energy plus the change in potential energy, or the change in mechanical energy. Since mechanical energy is defined as the sum of the kinetic and potential, the work done by an applied external force will equal a change in mechanical energy. Now, these two statements are for when we don't have friction. We will learn how to deal with friction a little bit later. So we'll do without friction first and then see what happens when we have friction. All right, so how about if we lift an object by an applied force, we change the potential energy of the object Earth system. So if I lift a barbell up in the air, I'm an external force to the barbell Earth system, and I change the potential energy of the barbell Earth system. The work done by my applied force then equals the change in the kinetic energy plus change in potential, or the change in the mechanical energy. All right, now notice that our work energy theorem still applies. So the work done by the applied force plus the work done by gravity equals the change in kinetic energy. So we solve for the work done by the applied force, we get the change in kinetic energy minus the work done by gravity. Well, we defined the change in gravitational potential energy as the negative of the work done by gravity, so work done by applied force equals the change in the kinetic energy plus the change in the gravitational potential energy. So the work kinetic energy theorem still applies. Now let's look at what happens if we have friction involved. So here we are pulling a crate across a horizontal surface where there is kinetic friction between the crate and the surface. So where are the applied force F pulling the crate to the right? Well, kinetic friction, of course, acts between the block and the floor, and we will assume the kinetic friction is a constant force. Well, we can apply the work energy theorem, since we showed before that the work energy theorem still applies in this energy conservation idea. So the net work then equals the change in kinetic energy. Well, I have the work done by my applied force, force times distance, minus the kinetic friction times distance. Now that is negative because the kinetic friction is acting opposite in the direction of the displacement. Our displacement is to the right, and the kinetic friction acts in the opposite direction. So when I do the dot product between the kinetic friction force and the displacement, I get the negative. So that's the net work then, F times d minus the kinetic friction times d. And that will equal the change in the kinetic energy, which is 1/2 mv squared minus 1/2 mv initial squared. So then I solve for the work done by my applied force, F times d. So when I move the friction term to the right, I get F times d equals the change in kinetic energy plus the frictional force times the displacement. So notice that the term on the far right is the negative of the work done by friction. Well, friction, of course, will cause heat. So this will cause an increase in thermal energy. Heat is a form of energy, so we call that thermal energy. And that is an increase in thermal energy of the system. So F dot D, of course, is the work done by the external force. So I have the force, external force times the displacement equals the change in the mechanical energy of the system plus a change in thermal energy. And that change in thermal energy is equal to the positive of the work done by friction. Or I can write it as the work done by my applied force equals a change in mechanical energy plus a delta E thermal, a change in thermal energy. So when we have friction, we can just add this extra term of delta E thermal. All right, so that will be the end of this video. In the next video, we'll talk more about energy conservation and do some examples of particular situations. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel and please subscribe. I hope you find my videos useful.